Good day everyone, welcome to today's lecture. In today's lecture I'll be showing you how to determine residence time using Aspen HYSYS. So we have our problem statement, which involves the production of ethyl ethanoate using ethanoic acid and ethanol. So we'll be going over to our simulation environment right now. So first we have to add the components involved in the reaction or in the process. In this case, it's actually a process that has a reaction. So first off, we add our acetic acid, ethanol, then ethyl ethanoate and water. We add all that to the component list. Then let's go back to the problem. These are our reaction kinetic parameters. Then the problem statement continued, says it is desired to produce 375 kg per hour of ethyl acetate from a feed stream consisting of 13 mole acetic acid, 35 mole ethanol and 52 mole of water. This feed stream is available at 100,000 kg per day. A single tube plug flow reactor with a length of 10 meters and a diameter of 1 meter is available for use in an existing chemical plant. Determine if it is feasible to achieve the desired product using this reactor. Also find the residence time in minutes. Our fluid package is NRTL. Then we have our feed properties and then reactor pressure drop. So we have added our components. Just click on add, then add your components from over here. So we have added our components. Then we have also added the fluid package, which is NRTL. If you can see my cursor, fluid package is NRTL. So the next thing is to specify the reaction involved in the process. So this is the reaction over here. So we'll be creating a reaction set for it in our simulation case. And then these are the reaction kinetics. Now we'll click on reaction, then we'll click on add, then we'll click on add reaction. Now for this particular process, we'll be using the kinetic model, and this is because the kinetic parameters are provided. So we'll be using the kinetic model. You just click on it, then click add reaction. Then we can exit this, and then we specify the reaction 1. So first off, we'll be adding our components. We have acetic acid first, then we have ethanol, then ethyl acetate and water. Then we'll now specify their stoichiometric coefficients. So you see that the balance error is 0. We've specified that. Then we can leave the forward order and reverse order values as default. We are going to, our base component is acetic, basis is molar concentration, then for reaction phase, we'll be making use of aqueous phase, because it says consider the reversible aqueous phase esterification. So we'll be making use of aqueous phase. Then we'll leave our basis units and rate units as default, while specifying the forward reaction and reverse reaction parameters. So for forward reaction, we have our A value. The value given here is for the constant, which is A. So it will be 8 times 10 raised to the power minus 6 for the first one. For the forward reaction, 8e minus 6, and then for the reverse is 2.6 e minus 6. Now, in this particular case, we were not provided with activation energy. We don't have activation energy values, so we'll make them 0 for both the forward and backward reactions. Just use 0 for both, because we don't have those values. Okay, so now by the time you specify all this, you have your reaction ready and fully specified. And yes, we have both forward and backward reaction parameters, because it is actually a reversible process. So that's why we have both the forward and the backward parameters. If it was just a forward reaction, you will not have the backward reaction parameters. Okay, so let's go back. Now the next step will be to attach the reaction to fluid package. You can do that by clicking add to FP. Click add to FP, then add set to fluid package. So once you do that, you can go back and view it. You will see that the heat of reaction has been calculated. It's usually calculated after you have added the set to the fluid package. Then we can now move over to the simulation environment. So in this case, we're using a plug flow reactor, because the problem statement said this feed stream is available at 100,000 kg per day. A single tube plug flow reactor with a length of 10 m and a diameter of 1 m is available. So we'll be making use of a plug flow reactor, which can be found in the reactor section of the model palette right here. So this is it. So we can start our specification. We could click on it and create streams from inside. So our first stream is feed. Then our outlet is product. Okay, so first things first, we'll specify the feed stream. You can just click on it. Then we have feed properties. We have 25 degrees Celsius, 1 bar, and then the feed stream is available at 100,000 kg per day. That's our mass flow rate. So for mass flow, we have 100,000 kg per day, right? So the default is kg per hour, so it converts it from kg per day to kg per hour, right? Then we have 25 degrees Celsius, and then we have 1 bar, yes, which is equivalent to 100 kilopascals. Okay, we are good. Then we have our molar constant, we have our mole fractions. We can specify that next. So we come over here, we have 13 mole percent acetic, 0.13. Then how much ethanol do we have? Ethanol is 35 mole percent. Then we have 52 mole percent water. 52 mole percent water, 0.52. Okay, our feed stream is fully specified. Now the bar here says requires a reaction set, so we'll go to the reactions tab, and then we'll add a reaction set, the one we specified in the properties environment. So you can do that by clicking the drop down right here, and then you click on set 1, which was the set we created, and then we now have a new info right here which says unknown dimensions. So we are going to specify, or we need to specify, the dimensions of the reactor. That's either the volume and any of length or diameter, or we specify length and diameter and calculate volume. So we can go to the ratings tab, yes, and then we specify whichever we choose to specify. But from the problem statement, we have length of 10 meters and diameter of 1 meter. So for now we'll be specifying that. So length is 10, and diameter is 1. Now it calculates the volume of the plug flow reactor because we specify length and diameter. Now we could also decide to maybe remove, let's say we remove diameter, and then we specify the volume. Yes, so if we remove diameter and specify volume, HYSYS automatically calculates the diameter. So we now go to the next, which says unknown delta P. So for the delta P, we are going to be using 0 kilopascal, user specified. You could also use the Egon equation option so that HYSYS can calculate the delta P for you if you do not have such value. Yes, we are making use of 0 kPa. So just enter 0 right here. Yeah, so once you specify pressure drop, the plug flow reactor is fully specified, right? There are a few other things you could actually specify as well if you want to. You could specify the nozzles. Then you could also add an energy stream if you feel there should be a temperature change as the reaction goes on. You could add an energy stream and specify it as well, but in this case we are not going to be using that. So now the whole process has solved. We can now go on to determining the residence time. But before we do that, we can check and see what we got from the whole process. Now the first question though says determine if it's feasible to achieve the desired product using this reactor. The desired product is 375 kg per hour of ethyl acetate. So we need to go and find out how much ethyl acetate was produced from the process. We can do that using the workbook. Okay, let's use the workbook. Let me see. Go to setup, and then to material streams we can add the mass flow of ethyl acetate. So we click on add, then we look for master component mass flow, if we can find that. Let's see. Yes, master component mass flow. Yes, mass flow. Sorry. Master component mass flow of ethyl acetate. We add that and then done. Then we can go back. Let's see. Okay, so this is the master component mass flow of ethyl acetate in kg per hour, and we have 455.38, which is even higher than the desired product. It's higher than the desired product, which is 375 kg per hour. So we can say it is actually feasible to achieve this desired product at these particular process conditions that we specified for both the feed and the plug flow reactor, right? Based on what we are getting, which is 455.38 kg per hour. Okay, so that's for the first problem. Then for the second one, we are trying to determine the resident time in minutes. Now we can use the spreadsheet to calculate that. We could actually use the spreadsheet to calculate that. Now if we get out the spreadsheet right here, then we click on the tabs at the top, click on spreadsheet. Then we have to import some values that will help us calculate the residence time. Residence time is usually reactor volume over volumetric flow rate. That's usually the formula. So we'll be importing those values from the flow sheet. So first is let's say reactor volume, then the volume flow rate. Then residence time. So for reactor volume, you would have, you right click by the next box, just right click on it, then click on add import variables. So for the first one is reactor volume. We'll click on our reactor PFR 100, then scroll down. Okay, so this is the reactor volume right here. Then you click here, then click done. So this is the reactor volume. Then for the volumetric flow rate, you right click again, then you click add import variable. Now it will be the volumetric flow rate of the product actually. So you click the product, then we search for liquid volume flow, then STD ideal, then we also add it, then click done. Now we will now create our equation that will solve the problem, which is reactor volume over volumetric flow rate. So we would have B1 over B2, B1 over B2, then we close the bracket, then we multiply by 60 to convert to minutes, because volumetric flow rate is meter cube per hour. So we multiply by 60 to convert to minutes, then we click enter. So this is your residence time in minutes, 101.5 minutes, right? So this is how you calculate it using the spreadsheet. Now we can do one last thing before this video ends. Let's quickly do a sensitivity analysis on this particular simulation. Now to do sensitivity analysis, you just click on case study, which is in your home tab, right? So you could use Aspen HYSYS to do a sensitivity analysis. You click on case study, then you click on add. Now the case study we'll be working on will be a study of reactor volume against conversion. Reactor volume against conversion. We'll see how the reactor volume affects the conversion percentage. That's what we'll be doing in this particular case study. So find variables. Independent variable will be reactor volume. Okay, so this is reactor volume. Done. The independent variable is the one you specified. The independent variable are HYSYS calculated values. So for this one, it's conversion, and conversion will still be from the PFR, the reactor actual percent conversion, and then click done. So our current conversion value is 31.77. Now we go to case study setup. Now it's in the setup that you choose what kind of case study type you want to do, and in this case we want to do a sensitivity analysis. So you just scroll down and click on sensitivity, or whichever one you want to do depending on your decision. You just choose that particular one, but in this case I want to do a sensitivity analysis, so I click on it, then I specify the range. Okay, so for this I'll use 1 meter, then here I'll use 80 just for illustration, then step size of 5. So we have 16 steps. Then I can click on run. Okay, so it says success. So the analysis has been done. I can click on results. These are the results of the analysis. Then we can check the plots as well. So this is the plot right here. Let me see. Okay, so this is a plot of conversion against reactor volume. So initially an increase in reactor volume actually yields an equivalent increase in conversion until you get to about 50 meter cube or so, then it begins to balance and there is no much increase beyond that. We can also understand that better using the results, right? So from at about 50 or so, you see that the conversion does not really increase so much. You see that. So this is how to actually do a sensitivity analysis on your simulation. At this point, we have come to the end of this particular lecture. I hope you gained some knowledge, right? So I would expect you to give your observations and comments in the comment section. You could like the video as well, and then subscribe to get notifications in the future for upcoming lectures. Thank you everyone, and have a good day.